Welcome back, everyone. This is lesson 6 of radioactivity. It's actually a separate topic of radioactivity called half-life. So before we start, can you please make sure you've put you turn to page 39 and just write lesson 6 and the date at the top of the page. And in terms of the title, well, it speaks for itself. It's half-life here. And before we go any further, we'll just have a look at the specification, the spec for half-life. And we're going to split this 4 spec statements, and we're going to cover 2 of the statements during this lesson, and then 2 in lesson 7 to complete the booklet. Now we're doing pages 39 to 46 as highlighted there. Now before we start, let's just highlight what we're going to be learning today. This section D, or spec statement D, the different uses of radioactive materials, we'll be starting off on this firstly today, where we'll be looking at biological effects and how they can be used to treat humans and animals. But you're also going to be covering that section in your next lesson as well, in lesson 7. So part D will span lesson 6 and 7. We're looking at section C as well, which is how to perform simple calculations involving the activity and half-life of radioactive materials in a variety of contexts. So what you need to be able to do is calculate the activity after a certain number of half-lives, or calculate the half-life from a given data, or on changes to activity. So what on earth is this idea of half-life? What does it mean? A little bit of a clue there for you. There's its definition. The half-life is the length of time it takes for half the atoms in a sample to decay. It's a constant for a particular element. Half-lives vary between different elements from seconds to billions of years. So the actual definition is in that first sentence there, up to the semicolon. Half-life is the length of time it takes for half the atoms in the sample to decay. Just bear that in mind. Before we go any further, let's just look at an application of a radioactive isotope, or radioisotope, and how it can be used to treat, in this case, a horse. I'd just like you to read the rest of page 40, and I'll put a line across the page where I want you to read just down to there, and learn how this particular radioisotope, I believe it's iridium, is used to treat horses with this particular medical condition. So just pause the video now, and when you get to this line, press play again. Okay, I'm going to take it from below that red line. The radioactive isotope used on the horse was iridium-192. It has a half-life of about 75 days. This means that after about 75 days, the radioactivity of the iridium needles have halved. After about 375 days, about 5 half-lives, the radioactivity levels will have dropped to a normal background level. Remember we talked about background level, background radiation, and in Pontidilis is about 17 counts per minute. and the iridium will no longer be considered radioactive. Now, before we fill this table in, I just want to to introduce this concept of half-life. Now, I made a few notes here. You can see this this lady in the bubble bath. Now you can think of half-life. If you poured yourself a bubble bath and there were 1 million bubbles in this bubble bath, and you were able somehow magically to count each one of these bubbles. So you start off, you pour the bubble bath at 7 p.m, 7 o'clock. And let's say 20 minutes later, those 1 million bubbles, so by 7:20, those 1 million bubbles have reduced to 500,000 bubbles. We would say the half-life of that bubble bath is 20 minutes. So think of each one of those bubbles as an atom. And every time a bubble bursts, pop, it's like an atom decaying. I had to include this photo here when I looked on Google Images for bubble baths. They're having a whale of a time. Look at that bubble bath. I'd imagine there's about 5 million bubbles in there. But even if there were 5 million bubbles, the half-life would still be the same. If it follows the same model, that 20 minutes later, there'd be 2.5 million bubbles left if the half-life of this particular brand of bubble bath is 20 minutes. So let's think about that analogy, because sometimes analogies are very useful to understand new ideas, new concepts, by transferring an understanding of something like a bubble bursting can help us understand an atom decaying. We're going to look at a simulation now to get a deeper understanding of exactly what we mean by an atom decaying again. Now let's look at the simulation. I'm going to choose actually a carbon-14 atom. So a carbon-14 atom is called carbon-14 because you've got 14 nucleons in the nucleus. That's going to be a combination of protons and neutrons. And over time, remember that this is a radioactive atom or a radioisotope, meaning there's too much energy in there. It's too unstable because of the imbalance of neutrons and protons. If you look at the top here, we're simulating what could happen to this atom over time. At some point, that atom is going to decay. Just like a bubble in a bubble bath could pop at any time. You don't know which bubble is going to pop next. And in a sample of carbon-14, you don't know which carbon-14 atom is going to decay next. I'm going to click on play at the bottom here. And I just want you to keep your eye both on this atom and what happens here. Okay, look what happened. It changed from a carbon-14 to a nitrogen-14 atom, and you could see that this atom jumped from there to there. If we quickly go back to our notes, you can see that if we were to show what's happened, we can see that the number of protons in the protons in the carbon atom was 8, and then it turned to 7. So a proton has actually changed to a neutron, because we had 6 neutrons, and 7 plus 7 gives you 14 neutrons. And a beta particle was emitted with a charge of -1. Now, look, that decayed on, it's not quite 5,000 years. It's 3.147 thousand years, is a strange way of showing it using significant figures. So 3,147 years that particular atom decayed. If we did it again, reset the nucleus, this time it's decayed at a different time, 1,500. Look, it's a random process. I could do 3, and look at this time it's gone 8, 9,000, 10,000 years, 12,000. It's still going. It's gone off the screen. 8,000, 9,000, 20. So it's a totally random process to find out. Look, it took 24,000 years for that particular carbon-14 atom to decay. But on average, the half-life of carbon-14 is here. What is that? That's about just between probably 5,000, 6,000 years. Now, so we can't just look at one. That's why you'd have to take lots of repeat readings to get the average. Now that will take a long time. But what we can do is use this here, and we can have 10. We can have 10 atoms, right? Look at this model here. We've got 10 carbon-14 atoms, and randomly different ones are popping like your bubble bath, or almost like popcorns. And you can see the electrons being kicked out. And how many we've got left? We've got one. No, we've got 3 carbon atoms left. And up to the half-life, out of the 10, 4 have decayed before, so we must have 6 are going to decay after. On average, you'd have 5 decaying before that red line and 5 after, with an average half-life of somewhere around here, again, around 6,000 years. Now, we're going to reset it all, and this time we're not going to have 10. We're not going to have, well, we got hydrogen. You could do the same with hydrogen, look, but hydrogen's got a totally different half-life. It's got about 12,000 years. And you can see out of the 10 atoms, 7 have actually decayed before, and we've got 3 after there. I'm going to reset again, and this time I'm going to choose carbon atoms, reset all nuclei. Yes, please. Yeah, reset them all. And I'm going to add in 10, 20, 30, 40, 50, 60. Watch this. It's telling you up here from that 60 how many hydrogen atoms you. So we'd imagine we'd have about 30 left when it reaches this red line. Let's see what happens, because you should get a more accurate value with a larger sample. You'd have learned about that in numeracy. Oh, but 32, look, almost exactly. Lots of fun here. Now I'm going to pause that, reset all nuclei, reset all. Let's do carbon again, and I don't know how many. Let's go for 100. So if we put 100 on the screen this time, press play. Now we should find, as this comes across here, 50 should decay when it hit around about 50, give or take a couple, when we hit half-life. And this little pie chart here should have gone around halfway with 50 carbon and 50 nitrogen. Let's go for it. I'm going for 100. It doesn't let me though. hold it at the start and we'll wait for all hundreds. So here we go, 10, 20, 30, 40, 50. No, it doesn't let me go more than 50, unfortunately. Oh, yes, it does. 90. I've emptied the bucket. So what's half of 90? 45. So what we should find is when we reach here, we should have 45 carbon and about 45 nitrogen. Oh, we've got 100 in that because it's 50-50 split, almost exactly there. Okay, so we did manage to get 100 carbon atoms. So before we carry on, make sure, like some are still decaying, make sure you've got this understanding of what half-life actually means. It's the time taken for half the atoms to decay. Now, turning back to your booklet, and remember now you're on page 41, let's apply that to this data. Remember that the half-life of iridium is 75. So after 75 days, we would have half those atoms would have decayed. But what we do instead, we measure the amount of radioactivity with a Geiger Muller tube, and we're not counting the number of atoms but the level of radioactivity, and we're finding that we've got 384 counts per minute at time 0, but it's telling us assume the background level is 12, so we're going to take 12 away from each reading. Now after one half-life, we have to halve this value, look, 372, to find out what's the reading after 75 days. So all we're doing is dividing 372 by 2, and that gives us 186. Change my pen. So it's 186. And I'd add on 12 for the background level. I'll do one more. After another half-life, that will be 2 lots of 75 days, that's 150 days. I would now divide that 186 by 2 again. That gives us 93. Add on the 12, the background radiation, that's given us, not 95, 105. Now, I know we can't get half an atom, so what we'll do, we'll round up. Divide by 2, 46.5. Well, I'll write down 47. Oh, 225. And add on 12 to the 47, that's going to give me 59. I'll let you do the last two. So pause the video now, complete the last 2 columns, and when you've completed the last 2 columns, press play again. Okay, so that's what you should get when you work it through. Interesting question underneath. You don't want the radioactive sources to have too short or too long a half-life. Well, I'll give you the answer here now verbally. You can write it down yourselves. You don't want the half-life to be too short because it won't be effective enough to treat the horse and get rid of his ailment, his sarcoid. He won't be able to go from there to there because it takes a certain amount of time to get rid of that growth. you don't want it too long, because after the radioisotope has healed the horse, you don't want then to expose the horse to unnecessary radiation, because it may have an unwanted side effect on the horse, an unwanted health side effect on the horse. So you want it somewhere in the middle, almost like the Goldilocks zone. Not too long, not too short, just right. So it says, in fact, iridium has a long enough half-life for it to be transferred from the nuclear reactor, where it's made, to the surgeon for insertion into the sarcode for 4 to 14 days. After this, the horse can recover and iridium returned to the reactor. Okay. Turn on to the next page then, please, page 42, and just pause the video and read that paragraph there that just reinforces what we've already learnt. And when you've done that, in your own words, can you just fill this here, explain what half-life is? If you remember, there is a definition in the chapter summary that can help you if you can't remember yourself. Okay, so pause the video and do that now, please. When you've written down your explanation of half-life, press play. Next, we're going to learn that different radioactive atoms have different half-lives. Isotopes with very long half-lives remain radioactive for a very long time, whereas isotopes with very short half-lives only remain radioactive for fractions of seconds. We looked at hydrogen and carbon a few moments ago and saw the same thing underneath here. Look, if we take boron-19, it's got a half-life of fractions of a second. Remember, 10 to the minus 3 is a millisecond, a thousandth of a second. So boron is going to lose half its radioactivity within a 3,000th of a second. Whereas if we go to the total extreme, we've got another isotope here, tellurium-128. What's that? 10 to the 24 years. Billions of years. If we've got somewhere in the middle, carbon, we've got carbon-15, we've got carbon-11, but no carbon-14. Remember, carbon-14 is the one we looked at a moment ago. So all these different radioisotopes have got different half-lives. Just fill this in next. The time for something, the number of the same type of radioactive atoms in a sample to decay. So the time for, that's going to be half. Wrong pen again. Select the right pen from the pencil case. Half the number of the same type of radioactive atoms in a sample to decay. Decay, remember, that's like the bubble bursting, or what we mean by decay is the atom gives out alpha, beta, or gamma radiation. We learnt about that a few lessons ago. Now, there's a way of recording we're on the next page, by the way, now. Recording the activity of a radioactive sample. And the unit we use, it's a new unit you wouldn't have heard before, is the Becquerel, shortened to large B, small q. After this gentleman here, Henri Becquerel Esq, named in the honour of Henri Becquerel, who discovered radioactivity in 1896. So it's only been discovered, what's that, 424 years. An activity of 1 becquerel is equivalent to 1 radioactive decay per second. which is quite a low value. Right. A 0.5 gram of iridium will have a total activity of, look at that. Oof. If we were to put a number on that, how many, we learnt in year 10, remember now about how we can use prefixes and significant figures. We'd have to, I'm starting the wrong side. What we need to do is start on the right hand side. We've gone 3, 6, 9, 12. That's 160 times 10 to the 12 becquerels. And remember this, you've got at the front of the booklet 10 to the 6 is mega, 10 to the 9 is giga, 10 to the 12 is tera becquerels. Oh, there we go. Oh, I just spoiled your fun. Question 1. It says, write this last becquerel value down in standard form. Well, if we're using a prefix, we can do the 160 tera becquerel. The standard form, remember, you put one number before the decimal point, 1.60 times 10 to the, pause the video and do it yourself. What you should have found out is that there should be 1.6 times 10 to the 14. If you think about it, if you compare it to 160 times 10 to the 12, you've got two aspects to this number. You've got that bit and that bit. So if we make in that part, I should say, 100 times smaller, we need to make this bit 100 times bigger. Yeah, people think of it in different ways. That's the way I think of it. So I'd like you to answer question 2 and 3. I've given you a really big help. More than a hint, really. You should be able to answer those. So pause the video and press play when you've completed 2 and 3. Okay. Can this value be written down as this? 160 times 10 to the 12. Well, yes, I've shown it up here. So the answer to that would be yes. Write down the value in question 2 with the correct prefix. Again, that's done up above there. So it would be 160 tera becquerels. A Geiger counter will measure a far smaller activity rate than the actual rate. The iridium wire emits beta particles. Why does this occur? Well, it's because if you think about it, I'll use a different colour just to try and show this. This sample of iridium, it will be emitting radioactivity in all different directions, just as the sun shines in all different directions, and only a small amount will actually go into the Geiger-Müller tube. But what it does, it gives us an idea as to the level of radioactivity. So your next question is, why does this occur? I've just told you why. I want you to write that in your own words at the bottom of page 43. If you didn't get it first time, please just rewind, listen, and write it down in your own words, and just do that here. When you've done that, turn over please to page 44. And before we answer these questions, or you're going to answer these questions I should say, it's quite a few, we're going to look at another simulation to help you understand these graphs. It says the radioactive decay graph of iridium below shows how the activity of a sample of iridium 192 varies over time. Now you can see in the graph at the start the original value was 500. What we class as the half-life is the point at which half the activity has decreased to half the original value. Or the other definition, remember a half-life is the number of atoms that decay to half its original value. So if we extrapolate from half of 500 is here, 250. We go across from 250, see where it hits the curve, then we go down. And that's smack bang look in between 50 and 100. So I would say that's 75, the half-life of this particular radioisotope, iridium-192, we found out at the start, was 75. Let's look at the units, days, 75 days. So half the initial activity, we say is 250, remember the units, there it is, becquerels, BQ. And the half-life is shown here, 75 days. You can answer these questions, but as I said, we'll look at a quick simulation first. So we've learned we can think of the decay or half-lives in two different ways, either as a number of atoms that decay in, or we can think of it as a measure of activity. So if you look at this case here now, we've got a dead tree, and the activity of this tree is being measured, albeit not using becquerels, but the percentage of the original. But we can come on to that in a moment. If we resettle nuclei, what I want you to do is just keep your eye on these red dots, and they turn in blue. Every time a red dot turns blue, that's modelling an atom decaying. So if it's decaying, it's going from a carbon-14 to a nitrogen-14 atom, and as that's happening, you can see the red's coming down and the blue's going up. The number of carbon atoms is reducing, and the number of nitrogens increasing. So the point at which we get to 50% here is the half-life of the carbon atom, shown here about 5,000. Well, in this case, look, it should be about 6,000, but in this case it's 5,000 years. But if we put more atoms in, we'll get a more accurate reading. That's a maximum number now. We should get a more accurate reading because we've got a larger sample. And because we've got such a large sample there, it's almost smack bang on what we'd expect. So again, the larger the sample, the bigger the more accurate, I should say, the measurement of half-life. Just to show that a different way, using a Geiger Muller tube, the tree, once it's got planted, will have 100% of its carbon-14, and when anything dies, plants or animals, the amount of carbon-14 decreases. That's why we do carbon dating, and we can work out the date of plants or animals this way. Don't worry about that. We're going to learn more about carbon dating in the next lesson, in fact. Okay, what I'd like to do now then, please, is to answer question 1. Question 2 is asking you to give step-by-step instructions of how to calculate half-life. I showed you a few moments ago, so you may need to rewind the video and listen to it again, and then write down. Remember, we do a method, number the different steps, and use command words or imperative verbs to use your instruction text as you've learnt over the last few years in school. Question 3. How long will it take a sample of iridium? Well, have a go at these. Try your best, and they will be self-assessment questions. When you've had a go at 1 to 4, press play, and we'll go over the answers together. Okay, what was the original activity? That's this value at the top here. That's 500, And remember, of course, to write down the units, becquerels. Question 2, I've already talked about to you how to do that. Question 3, how long will it take a sample of iridium-192 with an original activity of 1200 becquerels to reach an activity of 75? Okay. What you do is keep on halving from the original activity. So half of 1200 is 600 becquerels. This is quite a common exam question, and that'll be 1 half-life. 600. So I'm going to keep on doing that until we get down to 75. Okay, so I've got 1, 2, 3, 4 half lives, V as in plural, but it's asking how long. So what we've got to do is use this fact here that the half-life of iridium is 75 days. So the time will equal the number of half-lives 4 times 75, and then that's 300, so 300 days. Remember now, self-assess with, wrong colour, red pen. And if you just make sure you use that method when you're answering these questions. A sample of iridium-192 is an activity of 215 becquerels. 300 days after it was removed from the nuclear reactor. 300 days after. Now we know 300 days from here is 4 half-lives. How many half-lives have elapsed? Well, we know it's 4, but just to show it again, number of half-lives, lives, you would divide 300, that's the total time, by the duration of 1 half-life, and you get 4. Part B. What was the initial activity of the sample? So this time you're going the other way. On the question above, look, that was our original. So we've got to work backwards. So if we're going to work backwards in time, for every half-life, we've got to double from the value it's given us. It's saying it was 215 after 300 days. So we're going to double 215, 430, 860. I think that's that, but let's just double check. What's 860 times 2? 860 times 2, 1720 units becquerels, because that's 4 half-lives. What was the initial activity? It's always good just to be clear to whoever's marking your work, what's your final answer. Initial activity is that. Okay, question 5. Table shows a radioactive decay of a sample of iodine-131, and what does this mean? Well, its original activity was 800, after 4 days it was 566, after 8 days 400, and so on. Plot a graph of activity on the y-axis against time on the x-axis. Draw a best fit line through your points, and use your graph to measure the half-life of iodine. So you can do this now. I'll just do spoiling you, giving you the table again underneath. The axis is done for you. all you do, look, is you take each one of these points, so 0 and 800, and come up from 0 to find 800 is there. Next one, 4. You go up from 4, get your ruler, and 4 is, I'm gonna zoom in a bit here, this will help me. 566. So I gotta move my ruler, so that would be 4.5. Every small square is, I believe, 0.5. Let's just check, yeah. Because we've got 5 divided by 10. Every small square is 0.5. So 4.5 there, and so I'll do a little mark there to help me. But then we've got to find where's 566. So my 566, I use a thinner pen. Right, so it's here somewhere. That's my 4's there somewhere, but I can find 566. If I were to zoom in a bit more, that's 550. Every small square up is 10. So if that's 560, that's 570. My 566 is just about there. Okay. Now do that for the remaining 1, 2, 3, 4, 5, 6, 7 points. And what you do then is draw a curve of best fit. So pause. Sorry, slight glitch there. I've gone ahead and plotted those points, and also in purple I've put in a curve of best fit. So check you've first of all got those points in. If I just remove that curve of best fit for a moment, that's what each of your points should look like when plotted. And when you come to draw this curve of best fit, I've written on the tip on the right hand side there, it says turn the page to help draw the curve of best fit. Use your elbow as a pivot. It's difficult to show that on the video, but if you can imagine, if I'm drawing this curve naturally for me, because my elbow's at the bottom of the screen, my natural pivot from my elbow is this way. So in order to draw a curve as it is in the graph paper there, I would just rotate the paper. So I can put that curve of best fit back in again, and you won't be able to see it, but I'm actually turning the screen now, and when I draw this curve of best fit, I'll just check I got, yeah, that pen's about right. Obviously what you would do, you would plot this using a pencil, and I'm just looking at that, making sure I get through as many of those points as possible. It was not bad. It's not the best either, because you notice there's a few kinks here. When I say here, let me just circle them. Bit of a kink there. But look, you're not going to lose any marks for that. What you mustn't do is draw multiple curves of best fit. So what's a multiple curve of best fit? Well, it's where you start drawing a line like this, and then you draw another one here, because that would be a multiple line. Because if you were to imagine, right, the value for time here at 11 seconds is giving us two different readings for activity. It's giving us 350 and about 330. So that's one thing you mustn't do. So again, just do your best. Turn. I'll give it one more go now. Get what will be my pencil, and again, don't don't worry if it doesn't go exactly through all the points. You're just looking for a curve, because what the curve is showing is a relationship between time and activity. Let's look now at the last part of the question, part C, and just highlight it. Use your graph to measure the half-life of iodine 131. I don't want to spoil your fun and show you the answer first of all. I will go over it after, so I'd like you to have a go now at working out the half-life of iodine. So just pause the video now, please. Okay, now you've got to go at doing that yourselves. What you should have done, first of all, is just ask yourself, right, what's the, remember half-life? Half-life is the time taken for the number of atoms to reduce by half from the original value, or, in this case, the activity to reduce to half of its original value. So half of 800 is 400. To work out the half-life then, get a ruler, a thin pencil, and then you just extrapolate that value from the graph. You come down from that point there, and I would say I'm going to draw a thin line down from here. Then where's it gone through the horizontal axis? We're going up, remember, in 0.5s, so that would be 7.5, this would be 8. Okay, so the half-life would be 8. And the units we're dealing with here are days, so 8 days. Make sure you write that underneath for part C. But before we finish, because we're almost at the end of today's lesson, I just want to point one thing out. If we were to have 400 again, obviously we get 200. And if you were to do the same, work out what time it takes to get to 200. Just need to change my pen. What you'd find is that it would now be 16, because here's our first half-life to 8. There's our second half-life. I'll write underneath. So I could do first half-life, second half-life, and you could do the same. You could go to 100, even 50, and how long would it take then in order to get to 100? Well, if you spot the pattern, you should notice that it would be 24, because 8 on another half-life on top of 16 would give you 24. So that would be just about there. Now we're going to be using that concept in our final lesson of half-life and indeed radioactivity, because this is what we use in order to work out how old things are, such as a dead tree or an animal, and that process is called carbon dating. But I don't want to jump the gun. That's something to look forward to in our next lesson. See you next time. Bye.